So this is higher chemistry, and we're on unit 3, and this whole video is going to be about equilibrium. We should probably start with what is equilibrium. Well, equilibrium is something that only occurs in reversible reactions. So you're looking for that double arrow in the middle is an indicator that a question is going to be related to equilibrium. That's going to be your clue, because sometimes the word equilibrium is not directly used in the SQA question. So identifying that symbol is going to clue you in that you're potentially going to be asked something about equilibrium. And so it's for a reaction that is reversible. And equilibrium means that you've reached a point in that reaction where the rate of the forward reaction equals the rate of the reverse reaction or the back reaction. So that for every reaction going forward, there's an equal reaction going backwards at the same speed. And as a consequence of this, that the rate of each reaction is the same, it means that the concentration of your reactants and the concentration of your products remain constant. Because for every reactant turning into a product, there's a product turning into reactant. That doesn't mean that your concentration of reactants and products are equal to one another. They can be very different to one another. It just means that once you've reached equilibrium, they stay the same. And we can use graphs to represent equilibrium. So we have two different reactions, and you can see on both of these graphs, we've got a line representing the concentration of reactants in blue and a line representing the concentration of products in red. You can see that for each of these each of these reaction systems, the concentration of reactants starts very high and it drops, and eventually it reaches a level where it is constant. For the products, they always start off with a concentration of 0 because you haven't made any yet. And as time goes on, the concentration increases and it eventually levels off. The point at which both lines have leveled off and the concentrations of reactants and products are constant and not changing is when we've reached equilibrium. And so a dotted line has been put on there. This is a question you can be asked. You can be asked to identify a graph that represents equilibrium, or you could be asked on a graph to identify the time at which equilibrium was reached. And that's just the time where both lines have become straight, have become constant. You can also see that sometimes in equilibrium, the concentration of products is higher than the concentration of reactants, and sometimes the concentration of reactants is higher than the concentration of products. All that matters is that the concentration is constant. Reactants always start high, products always start at 0, and when the concentrations end up constant, that's equilibrium. We can also use graphs representing rate to identify equilibrium. So in this case, there's only one possible graph that you can get. One showing the rate of the forward reaction, reactants turning into products, and one showing the reverse reaction, or products turning into reactants. Equilibrium is reached when these two rates become identical to one another. So the two lines merge together. And remember, the axes in this case are different. It's rate against time. Now, the forward reaction always starts out fast and gets slower, and the reverse reaction always starts at 0 because, again, you haven't made any products for them to react at the start of the reaction. And equilibrium is the point at which the forward and reverse reactions have become equal to one another. So just like in the previous question, you could be asked to identify a graph that shows equilibrium for rate versus time, or you could be asked to identify the time at which equilibrium was reached for a system using the graph. And that's going to be the point at which those two lines have merged to equal the same rate. Another thing that is going to be really important, and probably the most common type of question you will get asked, is about the position of equilibrium and about manipulating or shifting the position of equilibrium. The position of equilibrium is just a term that helps us to describe within a particular system what the proportion of reactants compared to products is, because this is not equal for every equilibrium. It's different for every type of reaction. So here we've got two different systems, A being reactants, B being products. The one on the left, that equilibrium forms when you've got a low proportion of reactants and a high proportion of products. Whereas the one on the right, that equilibrium is actually established when you have an equal proportion of reactants and products. They are both at equilibrium, but they just have a different proportion of reactants to products at the point of equilibrium. Some reactions will favour products, some reactions will favour reactants. It is very rare to get that situation shown by the system on the right-hand side where you have equal numbers of each. It usually favours one or the other. And we need to learn how we can manipulate the position of equilibrium or shift it so that we can either make more reactants or products depending on what we want as a chemist. So we can change this. So the equilibrium position is constant, but if we change the experimental conditions, we can manipulate it to either produce more reactants or more products. If we want to make more product, we describe that as shifting the equilibrium to the right. If we want to make more reactant, we describe it as shifting the equilibrium to the left. So those are the terms that you want to be talking about, shifting the equilibrium left or shifting the equilibrium right. And the rule for how we do this is equilibrium systems always undo any changes that we do to them. This will make sense as we go through the examples, but equilibrium always undoes whatever change is put upon it. So the first one we can look at is temperature. So this is one of the different factors that we can use to change the position of equilibrium. So in a reversible reaction, one direction is exothermic. That reaction gives out heat and will raise the temperature of the system. And the opposite direction is endothermic and takes in heat, which will lower the temperature of the reaction. At equilibrium, they're balancing each other out and the temperature doesn't change at all. But one direction, exothermic, which raises the temperature of the system by giving out heat, the other direction is endothermic and it lowers the temperature. Each direction is always equal but opposite. So if we raise the temperature ourselves, if we decide to do the reaction at a higher temperature, the equilibrium will want to undo that change. So if we raise the temperature, the equilibrium will want to lower the temperature, and the only way it can lower the temperature is by doing more of the endothermic reaction, which takes in heat. And so the equilibrium will shift to favour the endothermic reaction. If we instead lower the temperature, the equilibrium will want to undo that change, so it will want to raise the temperature, and that will favour the exothermic reaction. If you can start thinking about these reactions in terms of what I did to the system, what needs to be undone, and how that can be undone, if you think about those three steps whenever you're answering any question on equilibrium, there is no reason why you can ever make a mistake. As long as you set it out logically, what did I do? What needs to be undone? And how can that happen? So here's an example. For those of you in biology, you might recognize this equation as being photosynthesis, but it doesn't really matter as a chemist what the reaction is. What we're looking for is that enthalpy change on the right-hand side. That delta H has a positive value, and that delta H written at the end is always for the forward reaction. So that's going from the left to the right. That delta H value represents the forward reaction. And in this case, it is endothermic, meaning that it's going to take in energy. So the question is, if we increase the temperature, what's going to happen? So remember, think about what we did, what needs to be undone, and how that will happen. If we increase the temperature, what needs to be undone is the increase in temperature. So the temperature needs to be decreased. So the system will want to undo the change, which means it will want to lower the temperature, decrease the temperature. Next step, how can it do that? Well, it can lower the temperature by doing more of the endothermic reaction. And in this case, that is shifting the equilibrium to the right to make more product, to favour that endothermic reaction. The next thing that can change or shift equilibrium is pressure. Now, just like every time we deal with pressure, it can only affect reactions that have gases. And this means gases at any point in the reaction. Okay? You need to remember for this the rule of molar volume, that if you've got the same number of moles, that's the same volume of gas. Now that's only same number of moles of gas equals same volume of gas. And we can change pressure by changing the total volume of gas. If we have less volume of gas, that means we're lowering the pressure. If we have more gas, we will raise the pressure. And remember, the system always wants to undo what we have done to it. So we're going to look at how pressure can affect equilibrium. So when pressure is changed, equilibrium will shift to undo the change. If we increase pressure, the equilibrium will want to decrease pressure. It will do this by making less volume or less moles of gas. If we decrease the pressure, the equilibrium will want to undo that, so it will want to increase pressure, and that means it would need to make more volume or more moles of gas. Pressure can only affect equilibrium if there is a different or an uneven number of moles of gas on either side of the equation. Okay, if you've got the same number of moles of gas on each side, changing the pressure will not be able to do anything. So we're going to look at 3 different examples and see, can pressure affect this, and in what way will it affect it? So here's our first example. We've got hydrogen reacting with iodine to produce hydrogen iodide. Will pressure affect the position of equilibrium in this reaction? So the way to do this is to look at the number of moles of gas on each side, specifically only the number of moles of gas. So on the left-hand side, we've got 1 mole of hydrogen gas and 1 mole of iodine gas. That gives us a total of 2 moles of gas. On the right-hand side, we've got 2 moles of hydrogen iodide, which is a gas, so that's 2 moles of gas. If we've got equal number of moles on each side, pressure cannot affect it. And so if you're ever asked a question like that, just say, pressure cannot affect because there's an equal number of moles of gas on each side. You have to specify that it's moles of gas on each side. Can't just say number of moles. Has to be number of moles of gas. We've got a second example here. You should be able to identify this as the Haber process. And again, the question is, will pressure affect the position of equilibrium in this reaction? Well, what we do is we look at each side and we look specifically for gases. On the left-hand side, we've got 1 mole of nitrogen gas and 3 moles of hydrogen gas. So that's a total of 4 moles of gas. On the right-hand side, we have 2 moles of ammonia, and it's a gas, so that's 2 moles of gas on the right-hand side. So we've got an uneven number of moles, which means yes, pressure can affect this reaction. So then we need to think about, in what way? Well, if we increase the pressure and use high pressure, the system will want to lower the pressure, and it does this by making less moles of gas. So if we increase the pressure and use high pressure, the equilibrium will shift right to the side with less moles of gas. If we did the opposite, if we lowered the pressure, decreased the pressure, the system will want to undo that. So if we lower the pressure, the system will want to raise the pressure, and it does this by shifting to the left and making more moles of gas. So remember, when it comes to pressure, more moles of gas means higher pressure. Lower moles of gas means lower pressure. Okay, I've got one final example here. Will pressure affect the position of the equilibrium in this reaction? So this is a reaction that's usually not in equilibrium. I've just said it's in equilibrium for this sake. But remember, we look at each side and we're looking for the total number of moles of gas. Now on the left-hand side, we have 2 moles of sodium solid. We have 2 moles of water liquid. That gives us 0 moles of gas. On the right-hand side, we have 2 moles of sodium hydroxide aqueous and 1 mole of hydrogen gas. That gives us 1 mole of gas on the right-hand side. Will pressure affect the position of equilibrium in this reaction? Yes. Even though there's no moles of gas on one side, there's still an uneven number of moles of gas. So it doesn't matter if there's no moles of gas on one side of the equation. As long as there's moles on one side, it's an uneven, so you can have an effect of pressure. So we need to think about how it's going to happen. Well, if we increase the pressure, the system will want to decrease the pressure, and it will do that by shifting the equilibrium left to make less moles of gas. If we did the opposite, if we lowered the pressure, the system would want to undo that, so it would want to do the opposite. It would want to increase the pressure, and it can increase the pressure by making more moles of gas, which would mean shifting the equilibrium right. Next factor, we've got 2 more to cover, is concentration and equilibrium. Now, concentration is probably the one that you might get asked most about because it can be the most complicated one to deal with. But don't worry, we'll go through it. If we increase the concentration of a chemical, the system will want to decrease the concentration of that chemical. Just always remember, equilibrium is undoing what we do to it. So if we have the Haber process, if we add more nitrogen to the system, that's us increasing its concentration. The system wants to decrease the concentration, so the way it's going to do that is by shifting equilibrium to the right to make more product. So when it comes to increasing concentration, it's very easy. If you add more reactant to the system, the equilibrium shifts to make more product. If you add more product to the system, it will shift left to make more reactant. However, it's not always going to be a situation where you're increasing the concentration. It's also possible to decrease concentration. And if we decrease concentration of a chemical, the system will shift to increase it. So again, if we looked at the example of ammonia, if we were able to just remove hydrogen from the reaction, the equilibrium would have to shift left to make more of it. Now, the reason why concentration is a bit more complicated is because it's not usually possible to just magically remove one reactant or product from the equilibrium. The way in which we do that is by adding another chemical which will react with either a reactant or product, and as a consequence decrease its concentration. And so you need to think about what is being added to the system, what could it react with, and as a consequence lower the concentration of that. So it's sort of like a 2-step process in order to work out what's happening. So decreasing concentration. As I said, it's difficult to directly remove a chemical from a system to decrease its concentration. You often have to add another chemical that will react with one of your reactants or products. So for example, if you want to make more product to shift the equilibrium right, you might want to add a chemical that reacts with the other one of your products, decreasing its concentration, and then the system will want to try and increase the concentration, so we'll shift the equilibrium right. And so you do need to be aware of what chemicals might react with chemicals in your system and be able to decrease their concentration. So the next slide is going to give you examples of the most commonly used chemicals and how they are potentially removed or decrease the concentration. So common chemicals. The prime two examples are acids and alkalis. If you've got hydrogen ions or indeed a general acid, if you added a base, an alkali, or hydroxide ions, it will convert that acid or those H+ ions into water. That is decreasing the concentration of hydrogen ions or acid, and so the system will want to shift to make more acid. So if you add base to an equilibrium that has acid on one side, the equilibrium will shift to the side with the acid on it. Similarly, if you have hydroxide ions or a base on one side, if you add acid to it, that acid will react and convert those hydroxide ions to water, decreasing the concentration, so the equilibrium will shift to make more hydroxide ions. Another good example is carbon dioxide. If you produce carbon dioxide gas, if you're able to bubble that through lime water, that's removing it from the system, and so the equilibrium will shift to try and make more carbon dioxide gas. Those are the most common ones. The other ones, which may show up in more older past paper questions, but don't tend to be on the newer ones, are dealing with metal ions. If you've got metal ions in one side of your equilibrium or your reversible reaction, if you're able to add an ion that will form a precipitate with that metal, you are decreasing the concentration of that metal, and therefore equilibrium will shift to make more of the metal. And if you've got a halide ion, so any of the halogens as an ion, if you add silver ions, again you'll form a precipitate. Those final two definitely show up in some of the early 2010 past papers. So just be aware of that. Now I know this video is a bit long, but we're on to our final one, which is looking at catalysts. Now, catalysts do not change or shift equilibrium at all. Catalysts only affect the rate of reaction. So catalysts, when they're added to a system that's under equilibrium, the catalyst speeds up both the forward and the reverse reaction, and they speed them up by the same amount. So what a catalyst does is help a system reach equilibrium quicker, but it cannot be used to shift the equilibrium left or right. How it does this is that a catalyst lowers the activation energy for the forward and the reverse reaction. So that's all you're doing, is lowering the activation energy of both the forward and the reverse reactions. And it will lower the activation energy of each one by the same amount, which is why all it does is keep the equilibrium constant. Okay, so that has been a summary of all of equilibrium. I know this is a longer video, but equilibrium is a topic that is very important. It's also really important for advanced higher because equilibrium forms a good third of one of the units at advanced higher. So it's really important that you understand it if you are planning on taking this forward. So I'll see you in the next video.